In this video, I will derive the famous var-of-par equations. So in particular, let's look once again at the equation y double prime plus y equals secant t. So as before, the idea is to look at the homogeneous solution, which was a cosine t plus b sine t plus b sine of t. And what's the idea once again is to guess your particular solution to be of the same form. So suppose, once again, yp of t is some function of t, so u of t cosine of t, plus some other function of v of t, so v of t sine of t. Right? Where u and v are to be found. U of t and v of t are to be announced. And remember this for what's to follow, because this is important. We don't need to find all the functions u and v that satisfy this. We only want one u and one v, because it is a particular solution. We just want one of it. Okay, well, since we have yp, let's plug this into the differential equation. Plug yp into yp double prime plus yp equals secant of t. And let's first differentiate yp once. So yp prime, that becomes, using the product rule, u prime of t cosine of t plus u of t minus sine of t plus v prime of t sine of t plus v of t cosine of t. And in particular, let's group all the derivative terms together and then the non-derivative terms. So this becomes, now write it in yellow, you'll see why, u prime of t cosine of t plus v prime of t sine of t. And then plus, I find minus u of t sine of t plus v of t cosine t. So that's the first derivative. And at this point, let's pause a little bit, because this already looks complicated. But so far, we're only doing yp prime. If we continue and do yp double prime, it would be a big mess, because we would have terms of the form u double prime of t, v double prime of t, which defeats the purpose, because our ODE is already a second order ODE. Why would you want to have something even more complicated? On the other hand, remember, we only want one u and one v that works. So it's okay to do a couple of simplifications, as long as we're guaranteed to find one u and one v that satisfies the equation. So just out of convenience, assume this term is zero. So out of convenience, assume this is zero. This is zero. Once again, and this is the part that confuses students the most, it doesn't have to be 0. There's no reason why we have to put it equals 0. We're just doing this out of convenience. If we find some u and v that works, then it's okay, because we just need one u and one v. Okay? If somehow we continue and we find there's no solution, then we would have to look back at our assumptions once again. Okay. So once again, just to simplify our work a bit and to not have u double prime and v double prime terms, we assume this term is 0. And this actually gives us, weirdly enough, our first equation of var of par, because then we get u prime t cosine of t, or if you want the other way around, cosine of t u prime t plus sine of t v prime t equals 0. That's already our first equation. Right? Functions and then u prime. If, by the way, this doesn't satisfy you, then wait a couple of lectures when we do systems of differential equations and do var of par there, then you will see how this 0 maybe more naturally pops out. In any case, anyway, on $4 a pound, what we then get is the terms in yellow, they're 0, and then we get that yp prime simplifies to just that second term. So what we end up getting is yp prime just becomes minus u of t sine of t plus v of t cosine t. And now we want to derive our second equation, where we have to look at the second derivative terms. Equation. So let's look at yp double prime. And that becomes minus u of t sine of t plus v of t cosine of t prime. And that becomes minus u prime of t sine of t minus u of t cosine of t plus v prime of t cosine of t. And I think minus v of t sine of t. And now what we want to do, we want to plug this into a differential equation, which remember said yp double prime plus yp equals secant of t. So let's look at yp double prime plus yp. Yp. So this becomes minus u prime of t sine of t minus u of t cosine of t plus v prime of t cosine of t minus v of t sine of t. That's yp double prime. And now yp is just u of t cosine of t plus v of t sine of t. Right, that was our original assumption. Now, notice two things that's very important. First of all, there are no second derivative terms, which is exactly what we wanted. That's why we had this assumption. And also, we have nice simplifications because this u times cosine cancels out with this, and v times sine cancels out with this. Now, here this is quite amazing, but really it follows because cosine and sine are homogeneous solutions. So because cosine of t and sine of t. Solve y double prime plus y equals 0, if you really wanted to do it generally. And therefore, yp double prime plus yp equals secant of t, then just simplifies to minus u prime of t sine of t plus v prime of t cosine of t equals secant of t. And we then get our second equation. So minus sine of t u prime of t plus cosine of t v prime of t equals secant of t. Da-da-dum. So that's our second equation. And to summarize, if you want to put it all together, what did we get? So our first equation, that was cosine of t u prime of t plus sine of t v prime of t equals 0. That was because of our simplification. And then once you plug it in, you get minus sine of t u prime of t plus cosine of t v prime of t equals to our inhomogeneous term, secant of t. And if you want to write this in matrix form, it becomes just what we wanted. Cosine of t minus sine of t, sine of t cosine of t. And then u prime of t, v prime of t equals 0, secant of t. Last but not least, how do we know this has a solution? Because remember, we said, well, even after the simplification, we hope that there's a solution u prime and v prime. That's basically follows from the magic of the Wronskian. So just in a couple of terms, cosine and sine dissolve the homogeneous equation. And then there's a beautiful fact that says this Wronskian, in this case, is never 0. So this matrix is always invertible, which you can see because the determinant here is non-zero, which means you can then solve for u prime and v prime. And then by integrating, you can solve for u and v. So even after the simplification, you're always guaranteed to have a solution. And this is our variation of parameters equation, and that's the t.